So we have a bunch of Tomcat instances. We want to provision, we want to scale, we grow that out. This takes significant amount of time to spin up an instance of a VM. The VM, I'm going to say it's slow, and it's all relative, right? But what we mean is it takes 30 seconds, a minute, a couple of minutes to spin up an instance of an operating system. That's not the thing in it. That's not the service that you want. It's the thing to enable that. It's the infrastructure. Super challenging. The challenge in this space is you have to know things. You know the exact name of things. You know the IP. And again, from a troubleshooting standpoint, if you're an ops person or a DevOps person, your favorite debugging tool is tail, and I need to know where to go to SSH to tail the thing, right? That tends to be the challenges that you have. And it's a lot like spinning up an instance of an application on your laptop and being prompted with this question: which core would you like to run on? This would be a really weird experience, right? But this is the first question you get when you throw something in a data center. It's like, whoa, how do you want to put this thing in? All right, so this is the general challenge that we have. And in the early days, we could talk more about elasticity. I'm going to bypass some of this. But we can get some bin packing. We can utilize the resources. If I spin up an instance of Tomcat, the VM might be 2 gigs. It might be using 1 gig. Frankly, there's 1 gig of memory, resources that it could be using for other purposes that are basically wasted because they're never going to be utilized within that virtual machine. So we can bin pack these things, whether in the VM or on bare metal, and start to utilize the data center in a more intelligent way. The first org that I'm familiar with that started really seriously taking this idea to the extremes is Google. When they came out in '98, there were some things that were hesitant on, right? Like revealing things, but they still wanted to kind of convey this stuff in an academia type way. So they were going to like UC Berkeley and saying, hey, look at what we're doing. And they had this thing called the Borg. And the Borg essentially was like, I'm using this data center, and our focus is search, web search. And I want to guarantee so much traffic for web search, so maybe 75% is web search. But I'm only utilizing 30% in a given moment in time. How can I leverage all of my compute power for business value? So they came out with another thing, right? They first introduced LXCs in '98 to the Linux community, which is super great. Now we have containerization type technologies. But they came out with a research paper called MapReduce, which was also interesting, which the genesis, of course, of Hadoop and that kind of technology. The thing that's fascinating is if you look at the maturity model of this technology that we're talking about right now, at the high end of that maturity model, you would have different categorizations of applications. You would say this is a guaranteed service. This is absolutely required for business value. And then you would have best of service. And the best of service would execute when it can, knowing that it could be evoked, it could be removed. And what would you do if it's working on something and it could be revoked? You would checkpoint things. You would save things to disk. Why? Because eventually you'll come back, you'll start up, and you want to start where you left off. So there's an interesting thing that's happening in our industry where we're looking at Spark and we're going, this is amazing. Spark is so much faster than Hadoop. We should switch to that. Well, of course it's amazing. It's running all in memory, and that's fast. It's super awesome. Except for if you were at the most mature model, you wouldn't be doing that. So the model we tend to see very commonly when we start to go into this space, we break out analytics from microservice-based architectures. They have their own cluster. They're both accounted for differently. They're both managed differently. And if you have a dedicated cluster for analytics, that's awesome. You're still learning, and you're probably improving your infrastructure. That's great stuff, but it's not the highest level of maturity. The highest level of maturity is this: learning to bin pack and leverage all resources in your data center to maximum business value. That's kind of the value of what the Borg. Eventually, they moved to a technology called Omega, which is in the same category of things, right? It's an orchestrator tool of sorts. So they came up with the Borg, which is super awesome. They were really leading the charge and still have, and that's kind of the value prop that people look at with Kubernetes. The assumption is that, well, they created the Borg, and so now they're taking the Borg and open sourcing it, and that's not true. But it's what we believe, and it's fine, it's whatever. They did add some real value in that prior to Kubernetes, we didn't have a concept of pods. And in their experience, they never released something into a production environment without having some ancillary container running with the primary container. And we could go through reasons and such, but the whole purpose of a sidecar, the whole purpose of the secondary container is for some ancillary value, such as analytics and logging and things of that nature that I want to share on multiple containers and pods. All right, so the idea, a thought experiment real quick. What's the difference between running, executing an application on a 100 core node, or running an application or set of applications on 10 nodes with 10 cores? And so from a resource standpoint, they're roughly the same. But one of the values I have if I'm running it on one machine is I say, just start this thing. And what we don't even think about anymore, but there's in the operating system, there's a scheduler. There's a thing that manages those details, which we lose as soon as we get into a multi-node situation, into a data center. And so the promise, if you will, of using an orchestrating tool, and I don't care whether it's Mesos or Kubernetes, the value is that there's a thing that can schedule for you. What it requires, and we won't be able to go into those details here, is some intelligence on annotations, details on declarative nature. If you want the thing to be self-healing, you have to be able to declare and organize a data center in an intelligent way. You need to be able to find and land things when a node needs an SSD card or it needs a GPU. It needs to know how to land there. It can't be, again, statically partitioned, statically assigned. And that's the first, again, on the maturity model, when people tend to get into Docker, the first thing they do is they go into a static world and they just, they shuffle, they puppet, an instance of Docker with something that runs on that given node, and that's the first step. That's fine. The next thing you tend to see very commonly is in the orchestration world. They're like, well, how can I assign this to that node? I have literally an IP address that I'm going to assign it to. Again, somewhat of a mistake, or one could say lower on the maturity model, right? You need something where it doesn't need a human necessarily to determine at every moment in time what is necessary for this given execution of this container. So the idea is to make all of these nodes look like just one giant computer, like we have an operating system with the scheduler. There are some nuances that we can't avoid, though, that must be evaluated and adjusted. So we'll talk through some of those things. If we look at the Mesos world, which I'll start with, well, let me pause for a second. Whether we're going to talk Kubernetes or Mesos, there are so many similarities, and I'll address a lot of those. For one, they all have a master node, or something that we're just going to call the master. The second is they all have worker nodes, or minions, or slaves, or whatever you want to call the things, right? But there's some node that is where the general compute will happen. They all have some kind of leadership election type capabilities. In the Kubernetes world, we're going to have etcd. I'm going to have slides on that in a second. In this world, we have Zookeeper. We have a quorum. If you're not familiar with this space, if you're a dev, you're going to have one instance of a Zookeeper. It's necessary. It's a necessary part of the infrastructure. If you're beyond dev, you're likely going to have 3. There are commonly, very commonly, organizations that have 3 instances in their production environment. But the magic number is 5, all right? The magic number is 5. And it sounds like a weird thing, right? But it's super, super simple. When you have either a leadership election or the need to verify or to assert that data is consistent, I need to have some vote in that process, so ability to have quorum. It always has to be odd, so that's the first thing. It's easy. If you have 1, well, it's easy to be consistent on one node. Beyond that, we're going to have 3, right? That's odd. And I need to be able to have consistency across 2. If I can have agreement across 2 things, I have agreement. That's the core concept. But why 5? I need to be able to take 1 down for maintenance, and I need to be able to failure, and I still have quorum. That's the only reason. So at the highest level of high availability, it's always 5. So back to Mesos. Mesos, you have a Mesos master. The one significant difference is it's written in C++. It's probably not going to change. That's the way it was started many, many years ago. I can't remember when it started, actually. It's in the mid-2000s, I think. The very strong difference is that in the Mesos world, the master has very little intelligence. It doesn't know. The only thing it can communicate is that a failure occurred or I need to schedule something. Something told it to schedule a thing to run, and it will then find a way to launch that onto an agent, right? It doesn't have any real intelligence. In other words, if the process were to fail in the Mesos world, the Mesos master doesn't know how to handle that. It knows how to communicate that. And then there's a second level scheduler that has the intelligence. So it was like building out this infrastructure abstraction that abstracts you from all the nodes that are out there. And it allows you to say, I want to run this thing, and I don't care where it runs, potentially. And it will just find a place to land it, and it will land it there. And if there's a failure, it will be communicated back to a second level scheduler, and it will handle those details. And so now the problem, somewhat of the problem, in the Mesos space is that I have a variety of different schedulers with different interests. I have a scheduler for running, like Marathon is a long-running process. That's the name means that, right? It's a long-running process. It's just always stay up. So its job is when Mesos says this pod failed, its job is to go, wait a minute, I want that running. And it says, start another one. That's its job. That's pretty much what it does. In the metronome space, it knows crons, so it knows how to handle crons. So all the variations that you might have in intelligence, or all the duplication you might have in intelligence, are spanned out across different frameworks. And that is the term we use, by the way, is frameworks. The framework is the combination of a scheduler and an executor. So you're controlling two things in the Mesos world. I have the need to schedule something. In other words, I want it to land on an SSD card, and I want it to consume this many resources. Now go ahead and do it. That's the scheduler part. The execution part is this has a very interesting way of spinning up, and I want to control that. It's very rare that people use that technology, but it's there and available. So that's the core concept in the Mesos world, and it should be very familiar, even if you're not familiar with Mesos, if you already understand Kubernetes. One of the things that I like to say in the Mesos space is just like in the Linux world, if you're looking at an operating system, you have this kernel. It's an abstraction from the hardware, which is awesome, right? There are lots of things I don't have to know because of this operating system. We then have an init system. Fortunately, in the Linux space, we've started to really standardize. There were lots of things at one point, but now we can say systemd pretty much is our init system, where we used to have system5 and a variety of other things. When you write an application and you run that application, say Nginx or something, it doesn't know about the operating system. It's not necessarily talking to the operating system. If you're compiling against the operating system, you're creating a driver. So if you're creating a driver, that's a very strongly different thing than just writing an app that runs on the operating system. So with that analogy in mind, I take it to the next level. In the Mesos world, Mesos is the abstraction layer. It abstracts you. It can be bare metal. It could be on VMs. There are a variety of different things, and you don't care. Frankly, it could be a mixture. It could be a complete mixture of things, VMs and bare metal, fine. We have an init system for, we could say that Marathon is that init system. And when you're writing against Mesos, if you're writing against Mesos, you're writing a driver. That means you're creating a framework. You're creating a scheduler. But most of the time, you're just spinning up an application that's running on it. So that's the analogies. It's very similar also within the Kubernetes space. I'm going to bypass this slide a little bit. The one thing I want to point out before I do is that there's one strong difference in the Mesos world from the Kubernetes world. And I would also claim that it has the ability, it enables higher scalability than we can see in the Kubernetes space, all right? Now, I told you, hopefully I informed you if you read the description for the talk, this is not a bashing system. This is, you can pick one or the other, and there's actually good in either one, but there's consequences. Is that fair? So in this space, when you're looking at scale, in the Kubernetes world, there's intelligence at the master that knows about all nodes, and it's so cool, right? And it really is cool from this perspective. It's easy to create something called a daemon set controller. In other words, something that says I want an instance of a pod running on all nodes. That's what a daemon set controller is. That is enabled by the fact that at the master, I can see all things. But there's a negative to that. There's a constraining element to that. I have to know all nodes at one node, right? There's a limit to that. In the Mesos world, what's significantly different is I actually don't know all of the agents that are out there. What happens is, you do at some level, right? But what ends up happening is you get requests in to say, hey, I could run something. Is there anything out there? We call them offers. So I have an offer that comes in that has a range of resources that are available with all annotations, And the scheduler would get that and goes, oh yeah, I could fit on this, I would love to use that. But the idea or concept that I want to run one thing on all nodes is really, really challenging in that space, because you could have a node that's available within the cluster, but the resources are consumed and you never get an offer from it. You just never even see it necessarily from a scheduler standpoint. So it's really strongly different in that perspective, but in some ways, you've pushed out scale, you've pushed out information to the edge of things, and it makes it more scalable from that perspective. All right, so I mentioned, just like the Mesos, I like to compare to the Linux kernel. You could, if you wanted to, go out to kernel.org and build your own operating system for your platform. But rarely does someone do that. There's just a lot of things you would need to know and do. What you prefer is to get an opinionated option of that. So you're going to go to Ubuntu or something like that, something that has an opinion that agrees with your assertion of what the world should look like, right? It's more beautiful when it looks with GNU or whatever. That's what DCOS is. Data Center Operating System is a packaging of Mesos in a very somewhat opinionated way. Right? That's the core of what it is, and it says here's the things and how they're configured, because there's a lot of configuration flags, frankly, in the DCOS world. Now, what my experience has been is that, in general, ops people tend to like Mesos and DCOS. I don't know if I could vouch for why necessarily, but in general, that's the feedback I get. They like it. There's a lot of configurations. They're fine with that. They want to be able to control a lot of timeouts and things of this nature. And they prefer it. But there's a problem. DCOS is super challenging to get it on one node, to get, we don't have like a Minikube or like a Kind or something I can run on one platform. So at the same time that ops people tend to like it, devs tend to not like it because they can't get the experience without being into a cloud situation. So we run into that challenge. All right. All right. 100% open source, blah. I don't know if we need to go through all of that. So the DCOS architecture, we have a CLI, just like you would expect for Kubernetes. Most of the things that you could do, we're going to compare some more things at the lower levels after we go through a review of Kubernetes. All right, Kubernetes. What's interesting is I was working on Mesos in 2014, when at the first DockerCon, it was announced Kubernetes. Eric Brewer came on stage and said, Kubernetes, and there was basically one commit or something in the GitHub. It was basically a thought, right? But man, has it taken off. It really has taken off in a great way. And the challenge, of course, from a Mesos standpoint, is that it has a large industry support. And that's one of the huge value props. Lots of documentation, a lot of people behind it. You got Red Hat, you got Google, you got a variety of clouds that support it. You can just run on top of Amazon and gain access to it. It's fantastic. Here's the architecture of Kubernetes. You'll notice it's roughly the same. We have a master, and we have worker nodes, or minions in the old days, right? From this perspective, what's useful to know, and it was also true for Mesos, that all the components that you see there, all the components on the master, are actually distributable. They don't necessarily all have to be on the same node. You could have them on all different nodes. But it's common to have an image that has all those things for a master, the things that a master needs, and it totally makes sense from a management standpoint. But just know I could run those completely and on their own if you preferred. Once again, we have etcd as our key value pair store and for management of configurations and such. You'll notice that there's some interesting comparisons, right? Again, for almost one for the things that we have here for Kubernetes versus DCOS. Some of that is DCOS specific, like Minuteman and a variety of things in that space that don't really come out of Mesos directly. All right. I hesitate to pause. I don't know if I have time. But we have the master node. We have etcd. Again, I have a number of slides that you're going to be able to use as a reference. Frankly, with the number of hands that I saw in here that are already running Kubernetes, I assume that you know much of this already. One of the things that's probably useful to know, and it's what I've been working on for the last 9 months or so, is the API server in Kubernetes is the gateway of communication for everything in Kubernetes. If you're going to write something to etcd, if you're going to have any coordination within the cluster itself, it's all going to come directly from the API server. But the value here, and this is one of my favorite parts of Kubernetes, is that it's extensible. Newly added in roughly 2017, it was announced in end of 2016 in December, is the ability to have custom resource definition. So I can actually create my own resource kinds. This is really a phenomenal aspect of what the server is able to do. Nothing like that in the Mesos world. All right? I can create my own scheduler, which is also really cool. And we do, at some point, when I get to controllers, we want to make some comparisons of schedulers and controllers, because in some ways, they're very similar. Controller manager controls all of the controllers that are part of the ecosystem. I'm going to jump past those. So that's the master node. All right, scheduling. If we have an orchestrator, the idea and concept is that we need to orchestrate things. What does that mean? I need to be able to say I have a pod, I want this to run within the cluster, I want 3 instances of this thing, and I want them across fault tolerance, or fault boundaries. So what does that mean? Well, it can mean a number of things depending on what platforms or what your infrastructure looks like. But at a minimum, we could say one fault domain is going to be a node, right? So I want them running or spanning across multiple nodes. That's the kind of thing that you want to be able to handle or describe. And what's super important about that is that I want to be able to describe that so that if a node were to fail, which means the process on that node is to fail, that it will self-correct. It'll just manage itself. It knows I need to launch another thing because we said we wanted 3 replicate sets and there's 2, but it also knows not to land on a node that a process is already running on. Those are the things that we want to be able to communicate or say or do. So in the Mesos world, we have this 2-level scheduling strategy. That is to say, we have schedulers that are dedicated to a specific way of doing things. So we have a Spark scheduler. It knows how to spin jobs out into the cluster and potentially even have affinity towards certain data resources and things of that nature. We have Marathon, as I described before, and it knows how to do long-running processes. It's entertaining to me because, you know, I don't know. It's entertaining to me. We'll see organizations heavily utilize Marathon. They're familiar with Marathon, and what they'll end up doing is they will communicate to Marathon, I want to run a job. So they'll run something that will die, and then when the job is done, they'll then tell Marathon to delete the application. So now you're using Marathon in a way it really wasn't designed for. Its purpose was long-running processes. If you want to run a job, there's a thing called Metronome or Chronos that does that kind of thing. So we see some interesting use cases within this space, but the core is it's a 2-level scheduler. There's a pro and a con to this, and the biggest con is that I have repeating logic, if you will, span across multiple instances of things. Multiple schedulers have the same interest, if you will, in how you handle an offer. All right, we talked about that. So we end up with something that has many schedulers. There is something if there's an intellectual property in an open source project, the one that I would claim in the Mesos space is a thing called DRF, which is, it's basically about resource fairness. Now, it's actually some interesting logic to manage this, but here's what we discovered. To me, it's fascinating. If all of the schedulers are hungry, and by hungry I mean they all want to launch something, then DRF is phenomenal. It's fantastic in being fair and giving an opportunity to some scheduler that may have been starved. It's not seeing something, it's not seeing offers because something is hogging all the offers. And DRF basically forces yielding to provide fairness. That's its function. That's built inside the core of Mesos. But what we discovered is something quite different and interesting, in my opinion. I've spent also, previous to that 9 months, the 6 months before that was all in high-scale testing. And by high scale, we were out on Amazon. We were typically at, 6,000 cores, 105 nodes, and just cranking things up. And what we found really is that when you have a lot of schedulers, the typical behavior is Marathon would kick in and it would launch something, but then it was done. And so to include it in the fairness loop is not fair, right? Because it's done. It doesn't have any interest or need to launch anything. And there's lots of schedulers or behaviors that are similar in nature. So we have We still use DRF in some cases, but it's switchable now to basically random. We have found random to be very effective. Also, there's an ability that when you've connected as a scheduler to Mesos, to suspend, essentially. It's basically like saying, I opt out for right now, I don't have any offers, and so it's not included into the allocation loop. All right. Kubernetes. Kubernetes is super interesting in this space. One of the things, probably my favorite thing, there's actually two favorite things in Kubernetes, but one of them is how it handles the event queue and how it cooperates for scheduling, and how the controllers are kind of myopic and still cooperate together. Because when I say launch a pod in Kubernetes, what happens? Well, let's say I'm going to launch a deployment. When I launch a deployment, it then talks to the API and says, create, you're posting a deployment, and it then registers and writes that in etcd. And there's something watching that, the deployment controller, and it goes, oh, you have a deployment. I need to take care of this. And it goes, oh, you know what? We need a replica set. So it talks to the API that says, create a replica set for me. And there's something watching that. It's a replica set controller. And it's like, wait a minute, there's a new replica set. I need to do stuff here. I see that I have this pod, and I have 3 instances of it. I need to write that. So it will post 3 times to the pod API. Again, all of this is against the API server. All writing to etcd, all watching for different events. And we have this chain of events that occurs. In order to land a pod, there's like something like 20 interactions that happen. But, and the deployment controller, it doesn't really know anything about launching pods at all. That would be the pod controller, right? It's a whole, the core controller. It's a whole different thing. So this idea in managing this intelligence, if you will, across event queues is really, really phenomenal. It's really great stuff. There's some interactions. This is actually a super simplified version of that, but it gives the point across. Okay, I'm going to pause for a second because I've been going really, really fast. Any questions about scheduling? Before I do, real quick, there's a strong correlation. People would say, hey, in the Mesos world, I have all these schedulers. Well, guess what? In the Kubernetes world, you have all these controllers, and they're roughly the same thing. There's some value in the Kubernetes world that I have one scheduler, except in the last couple of releases of Kubernetes, you can actually have now multiple schedulers, and there's a whole new world that hasn't really been fully vetted yet. When would you create another scheduler? Why would you create another scheduler? It's fairly simple to actually land one, and it's fairly simple to identify that this manifest wants to use it, but when would you do that? And we're still kind of in the early days of that, really. It's super early. I would know more, I would be able to communicate more about when I would create a new controller than a new scheduler. But the logic that you would have in the Mesos scheduler, in other words, the identification that I want to run a job, and when the job's done, I want to mark that as done, as opposed to restart, that's really what's happening with controllers in the Kubernetes space. It's roughly the same. Different mechanism for how it does it, but conceptually roughly the same. All right, a pause for questions. Oh yeah, I forget I'm in Scandinavia. Oh, you guys left, that's good. It's rare. All right. Well, rare in public, always happening in private. But. All right, let's continue. Let's see here, scheduling, failure modes. I'm not sure what I was going to say there. It's interesting. Let's talk pods. I want to talk about some really interesting differences, and it might be useful to you, I hope. So first of all, we have a need for containers, right? Here's one strong difference. It's super important to realize. In the Kubernetes world, you have the ability to configure what kind of container runtime you're going to have. It's typical to use Docker. It's typical also to use like Containerd. But you have options. You can configure it. It's part of an ops infrastructure issue. It's one of the question marks that an ops person would have to figure out, actually. What devs don't know is that setting up Kubernetes is challenging. There's a lot of things you have to figure out. One of them is what networking scheme you're going to use, what containerization runtime you're going to use. So there's a lot of things. The reason why one of the reasons I think people might like or ops might like Mesos is there, or at least DCOS, is the opinion is there. which is not always true in the Kubernetes space. Now, you can get a opinionated packaging, which is plenty of vendors who are willing to do that. So regardless of what your container runtime is, in the Kubernetes world, you're using Docker. From a packaging standpoint, the expectation is you've packaged it inside of a Docker, and it will pull an image, and it will run that within whatever container runtime you have. What's beautiful in the Mesos world, and super useful, I think, is that we obviously do that too. We've been doing that for a long time, but we also have the ability to run just a container without Docker at all. And what that enables, which is somewhat unique, is that I can have a legacy architecture, some Java application or a Tomcat application where I'm going to pull a tarball of Tomcat. I'm going to pull a tarball of a JRE. I'm going to create that when I stand up the sandbox, which is what's happening when I launch an instance of a pod. And I'm not forced to go into a Docker imaging situation. I can just leave it in my old legacy style of things, and that's totally doable. It's totally fine, super easy. So we have this ability in the Mesos world that just doesn't even exist in the Kubernetes world. And what it's for one, it was there prior to Docker. Mesos was running at Twitter years before Docker came out. So we've been containerizing in that space for a very long time. And it was just something we kept. But it adds value. It adds the value where I don't have to dedicate a team, force them into Docker in order to enable orchestration. We can just do it on the fly. Now, the negative, so to speak, is there's some value in Docker in that I have a golden image. I have an image that I know has gone through the whole pipeline of development, QA, and what have you, and I'm running the same image when I land it in production. When you're fetching and creating essentially your runtime within a sandbox, there's this impression that things are different because you're building it on the fly, if you will. But if you're using the same tarballs, it's roughly the same. I get the debate, but you should be aware of that. When we talk about containers and VMs, it's useful. Again, I might bypass this slide unless someone stops me. But this is probably the best slide that I found in the comparison of what we get with the VM versus a container. In the container space, you have this, in the VM space, you have this guest OS, and it consumes a lot of space. What we typically see, the infrastructure of IaaS or virtualization consumes somewhere between 10 and 15% of your data center. So you lose 10 or 15% of resources in your data center for the benefit of virtualization. But you also have another negative, and that is the startup of the guest OS takes tens of seconds. It's somewhat heavy. And one could also say that the image itself is heavy. It's large. It's usually a half a gig or bigger. It depends on what's in it, obviously. And then you're running on top of this host OS. And the benefit of the containers is we've gotten rid of that. We're just completely without a guest OS. Spin-up times are in milliseconds. The other thing that is somewhat foreign to people if you haven't dove deep into the technology is that in the Linux world, you are always running in a container. There's no such thing as not running in a container. The core of container technology, actually, I think I have a slide on this in a second, so I'll pause for a second. We had this idea of containers, and then we introduced this idea of pods. There's another interesting difference between Kubernetes and Mesos that's worth identifying. First of all, pods really is a technology that Google came up with, or a concept that Google came up with, and they're the ones that kind of introduced it to us as a community. And the idea of that is that I'm the virtual thing that has two containers in it. Let's just say one or more containers in it. Okay? And the idea also is that I have shared space. I can talk one container to another, and that we're sharing the same network space. And there's more to it than that, but for a second, let's just pause. So that's the idea of a pod. What is the difference now between the two? In the Kubernetes world, a pod is a pod. It's just, it's one unit of things. If a container fails within a pod in the Kubernetes world, it kind of depends on how you have things configured. But it won't exit. It'll just hang around. And this can be one of those failure modes that can be super confusing at first, is my pod is still there. What is going on? Oh, yeah, the container within the pod is failing. What can I do about it? Well, then you start to put in readiness probes and live probes, and you make sure that you have the live probes on all the things that you're interested in within the pod. And then you've hooked that ecosystem into the container or into Kubernetes that knows what to do. When the liveliness probe fails in certain ways, it will then reboot, essentially. It'll kill a pod and start up another one. In the Mesos world, technically, when we spin up a container, there's an abstraction, a word that we use called a task. There's a task set running. Now, why would we have this abstraction? Well, there's a couple of reasons, but the biggest one is we don't care. Like, you can create your own execution engine. Remember, we have this framework, which is a scheduler and an executor. So I have a special way of launching things. I could have an executor for which when I execute something, it literally is just a thread. It's not a process that's spinning up. So we have this word that represents something that is launched, it's a process, or it's a thread execution, and it's irrelevant. It's just a thing that happens. It's an execution that happens in some way. So there's this concept called a task, which, if you're using pods, is super simple, right? It spins up things in almost the exact same way that Kubernetes would. But since we had task around, in order to create pods, which came later in the Mesos lifecycle, we needed to create a group. And so we have a task group. Now, the only reason that becomes interesting is because I can have a task group, which correlates exactly to this, and then so I can mimic this, if I will. But the one strong difference is I can just add a task to a task group, which means that I can actually control and change the pod, if you will, through its lifetime, if that means something to me, which is interesting. It's something I can't do in the Kubernetes space that I can do. Now, from an ops standpoint, maybe you don't want to. The idea that you would have something that would change, that would be mutable, is offensive, right? So you want to be, you just want to be aware. But it's a skill or a technology that is possible that's not possible in the Kubernetes space. Now, I backtracked a little bit on they can talk to each other. They have one shared IP address within the, multiple containers within the pod share same IP address, blah, blah, blah. Here's the core of it. Frankly, if you boil down what a container really is, a container is nothing more than these two things. It is namespaces and cgroups. And the namespace is your view of the world from an execution standpoint. When a process stands up, it has a view of the world. The things that it can view is, what are my PIDs? What is my network? You could go through the list, right? So namespace is my view of the world, and cgroups is controls. It's what my limits in the world are. So I can have CPU sets, CPU groups, so in other words, CPU control. I can have memory constraints, things of this nature. That is containers. That's all of it. All the runtimes provide instrumentation to enable this behavior. So when we say we're running a Docker in a container, it's doing this. That's why you have to run Docker on a Linux platform, right? Because these technologies are Linux. Yes, we're trying to push into the Windows. Yes, we're trying to do things outside of this, right? But that's the core of it. That's what's happening. So when we say we have a pod, all we're saying is I'm going to spin up multiple instances or multiple containers that live within the same namespace. And that's all we're doing. It's super simple. It's insanely simple. I'm not sure why it's become so popular or why it's so fun. There's so much exuberance around it. We've had these things since '98. It's been a long time. All right. I talked about UCR. Mesos, the term UCR is Universal Containerizer. It's the thing that says you can run legacy things, you can run Docker things. It supports all of those details. Oh, one pause real quick. I said if you're running on Linux, you're always running a container. There is no such thing in Linux as running a process that doesn't belong to a namespace and a cgroup, ever, period. So the question that you might be asked, potentially, is, is there some overhead associated with running inside of a container? Well, let's go bare metal, blah, blah, blah. No such thing. You are always inside of a namespace and cgroup, period, on Linux, always. You're either in the root namespace and cgroup, which is not where you want to be, if you're spinning up production level, processes, but that's the core of it. Okay. We could talk about security. In the world of security, when it comes to containers, there are two basic technologies we tend to use. They're both Linux-oriented. You have seccomp and you have Linux capabilities, which can control certain aspects of what rights the process or the PID has within that space. They both exist in both worlds. So in fact, I was the one that wrote the marathon one inside of, and metronome, frankly, inside the Mesos world. Now, the one challenge you would have is this. In the Mesos world, you have it built into Mesos, but you need all of the schedulers to be aware of that. And as I said, you have multiple schedulers with repeating technologies. That doesn't exist. There are plenty of schedulers that are unaware of how to take advantage of those details. So there's some delay, which doesn't tend to happen in the Kubernetes space. Again, the pros and cons. Talked about sets of containers and task groups. I got the 5-minute warning. There are a couple of things I want to make sure we jump to. Ownership, yeah. Life cycles. Sidecars, okay. We talked about running another container within a pod, but there are some really cool things in the Kubernetes space we just do not have in the Mesos space. Not that it's not possible to create, just no one's taken the time to build it. So when you look at Istio, which I think is a pretty interesting and fascinating technology, you'll have a controller that uses annotations, and when I spin up a pod, it will see a new pod coming into existence, it will throw in an annotation, and then throw in a sidecar. Now, again, you could get into this debate, do I really want to mutate the thing I'm deploying in a unique way in a production environment? But once you grow to value this experience, that is one technology that's actually kind of cool, that I actually can spin up my Istio sidecar within a pod, and I don't even know anything about it within the manifest that I'm managing from a developer standpoint. So it's an ops-only kind of operation. It's super cool. So we have sidecars in the Mesos world, but the idea of having a controller or a scheduler kind of be that dynamic in this way is actually foreign. Again, the technology is possible. It's just someone has to write it, and it hasn't been done. I don't know if I have time to go through resource details. I will say that in general, they're the same. Mesos capabilities as far as resource limits and how they're managed are roughly the same. Frankly, the limits themselves are really containerization based, so it's happening at the operating system level. When we get to affinities, containers and affinity, we basically have the same kind of capabilities across both of these technologies as well. And what we're saying is, at the core is, in the Kubernetes world, I have node affinity, I want to be able to land, or anti-affinity. Again, I'll advertise something real quick if it's foreign to you, and that is there are certain applications for which resources become the way that you manage it. In other words, if I have a process or a pod that consumes 2 cores, and I have another process that wants 2 cores, and there's only 2 cores on a node, there's anti-affinity built in, right? It's been consumed. That said, there are plenty of things for which there are challenges or constraints that you need to be aware of. If you're running Hadoop or you're running HDFS and a name node is running and it's heavily used, that's super memory intense and has a lot of paging out the disks that occurs. The same thing is true if you're running Kafka. Kafka is going to have a lot of memory that's jumping from memory to disk, paging. That is a thrashing that occurs. You can consider that a resource, and you're going to want to put anti-affinity on those pods. They need to naturally know, without a human dictating from a static perspective that it needs to be here, it needs to be there, that these things should repel each other. They should never land on the same node because technically they are competing for the same resource. So I'll stop it there. I think I'm running out of time. From a scaling standpoint, and then I'll end, one of the things that we should take away is that there are some strong limits in the Kubernetes space. They're well documented, and you can get essentially 100 pods per node, where we've gone clearly well beyond that in the Mesos space. We did a lot of scale testing a year ago or so. And so we have significantly, I will say this, in people working in production, in the real world, we get significantly higher scale in the Mesos space and have for some time. That's why you see Netflix replatforming on top of Mesos. It's not the only reason. There's other reasons that I don't have time to get into, but Apple moved their entire data center to running with Mesos on bare metal, and there's super good value to that. It's super high scale. It's not possible in the Kubernetes space, right? And that's not to say one's better than the other. There's an opinionated approach in the Kubernetes world and documentation and consistency that I just can't get in the Mesos space today. So there's value in either cases. In the other category, there's extensibility, as I mentioned, and I am out of time, so I will just say tusen tak. I will be outside if you have questions. All right, thanks.